Back to my butthole channel. It's me, Ellie, and today we're going to be doing Unit 2, Ecology. Okay, Ecology, I don't care. Okay, so some of these questions I genuinely just don't understand. I'm like, there wasn't a better way you could have, summarized that? Not like summarized, stated that? But okay. Sir, hold on. Okay, let's start with this. So this is literally just kind of like, hold on. This is just birth plus, why am I even doing this? It's fine. Okay, that's just like birth plus immigration, and then death plus emigration. And basically birth and immigration are like two positives, and death and emigration are two negatives. So you add the positives and then you minus that by the negatives. And the information you're probably going to get is going to be like birth per year and death per year. So you already have like the per year part, so you're only worrying about like you know how it's like it's like for rates it's like blank over number of years. You're only worrying about the blank part. And for that you're doing the things coming in minus the things coming out to find the overall change. Calculate predicted population size from initial size and growth rate. Okay, so for this, I'm pretty sure what this is saying is like using this growth rate to find a predicted population size. And what you do is you'd take that growth rate and you'd multiply it by the number of years that you're trying to like go into the you're trying to like predict into the future, and then you're gonna add that to the initial size, basically. And like the initial size, how do I explain this? For the initial size, it's like there's like it's probably gonna be your most recent size, but if you don't understand this, don't listen to me. But you're gonna want to use like the most recent size and within your data that you're actually using. So like within like your what you use to find the growth rate, which for this doesn't really matter, but the most recent thing that you use to find the growth rate is that the change that you'd want to do. Because hold on, let's say that you're predicting like 20 years in the future, and then the change rate is like 5, so it'd be like plus 100. Let's say you started like with 2020, like this was the year that you used in your data, like you did like 1950 to 2020. Then you'd want to use this, because then that'd give you 100 years from 2020. But if you were to use like 2024, then that'd give you 100 years from 2024. So they're not the same. That'd give you like predicted, what am I saying, 100 years? That gets you 20 years into, this would be 2040, and then this would be 2044. So there's a difference. So you just make sure that you add it to like this one. That's not important if you don't like understand that, because he's probably just, Mr. G'day is probably just gonna like he's probably gonna simplify the data like as much as possible. My toes. So there's that. Okay. Predict and explain population growth curves. Okay, so for those, this is an exponential curve. This is a logistical curve. And then this is a logarithmic curve, and then this is a linear curve. And there's also like the boom and bust, which is like logistic, and then there's also like this one where it like evens out. And hold on, the boom and bust okay. These two are logistical. Like those two are logistical. Yeah. That's really it. And then like for these like different things, is there like a laser pointer? That'd be so cool. Oh wow, that's cool. So guys, if you care to find me western sky, what did I just do? Okay, is that like a spotlight? That's really cool. Sorry guys. Okay, but for these different curves, this is probably like the best example of like population spiking, like beginning to rise. Like it's gonna be exponential, but this is a good example of like the population like rising but then setting out because of carrying capacity. This isn't really like seen anywhere in nature. Well, actually, never mind. This kind of is. This is like probably like after it's exponentially rising and setting out. That's kind of what logarithmic is. But linear isn't really seen anywhere in nature. That's the one. But this is probably the most realistic. Oh, these two are probably the most realistic, like examples of like whatever population growth and whatnot. Okay. Estimate carrying capacities from population data. Okay, so that's like, it'll give you like some kind of random like graph, like maybe it could even look like, and then you're gonna have to find some kind of curve within this, and for this one it'd probably be around like that, like this. And what Mr. Goudet said is that he is going to like accept a really wide range of answers, so there's that. Calculate growth rate from population data. So it's probably gonna give you like x1 comma. Oh, I can just freaking type it out. Okay, it's probably gonna give you like oh, then I can't do the stupid thing. X1 minus x2. Oh no, comma. Sorry guys. Y2, y1, and then it's gonna give you x2 comma xy2. It's gonna give you something like that. And then what you're gonna want to do is you're gonna do y1 minus y2 over x1 minus x2. That's just what you're gonna do, like this kind of thing. It'll give you 2 points, and then you're just gonna do change in y over change in x. The change is the difference. The change is subtraction in a nutshell. That's all it is. It's just subtracting 2 values. If you don't get this, put that on your cheat sheet. Put it on your cheat sheet. Okay. Describe the difference between density dependent and independent. Okay, so density dependent things would be like mainly like resources, which essentially like ultimately is just competition. That's what density dependent things are, like competitive things that are competition, like food and like partners to mate with and like area shelter, space to live, like things like that. That's going to be very density dependent. Access to resources. However, density independent factors are going to be things like natural weather, like weather and natural disasters, and like forest fires, and like things that are just out of the population's control, like things that they literally just can't control. Okay, calculate population sizes from mark and recapture. Okay, so mark and recapture is, let's say like there were like you marked three bears. Three bears. You went out into a forest and you found 3 bears and you marked them. So that's out of like, you don't know how many, so it's just X, put a variable in. But then you come back and you find 2 of those bears marked out of like a sample selection of like 10. Okay? So now what you do is you'd cross multiply, so you get 2x equals 30. And then your population would just be 15. So that's how you do like mark and recapture. So you're capturing, like you're starting when you initiating, you just start and you mark whatever number of whatever amount of whatever species, you mark how many you went to, and you don't know how many out of, so you just put X, and then you come back another time, and then you gather like a collection, a sample, you collect some sample, you find a bunch of that species, you collect it, and then you're gonna see how many were marked out of the amount that you collected, and then you're just gonna cross multiply. Wow, amazing, fantastic. Okay, and then quadrant whatever is just like let's say this one has 2 and this one has 1, then the average is going to be 1. If you don't know how to do that, then you add the 2 values, and then you add the amount of values together, and then you divide it by the amount of values you added together. And then you're going to multiply that by the amount of quadrants you have, so the population would be, the estimated population would be 4 in this case. Okay. Okay, so for clumped, it's like, that's probably going to be like with the lack of resources, like there's only resources in certain accessible and available and like usable resources in certain places, while uniform is probably going to be like bobcats are very territorial, like they They're very territorial, especially. Oh, and important to realize, like, dispersal patterns are going to be in a single species. They're not going to be like multiple species. Sorry if you don't like. I hope like this isn't just like stating the obvious, but it's going to be in like only one species. I'm so sorry. I'm so sorry. Okay, but for uniform, it's probably going to be something like bobcats who like mark their territory and they have like their own little secluded areas to themselves, and stuff. So it's like competition between inside rather than like just like only limited resources. This is going to be competition within a population, and then or a species. And then random is like wind, like seeds, like the wind just blows it and it just goes anywhere. And then the downsides to clumped is that like you're not really using all of the space that you have, like you're only using certain like areas of that space. Uniform, the downside is like you don't have as many resources because you only have like the amount available in your territory and that's it. And then random is going to be like the downsides to that are like trees oh this I was like putting this one for trees, especially like they the wind blows them anywhere, and sometimes like the trees don't have access to sunlight because they're shaded by taller like trees that were already there, so they're just never able to grow and become trees, so that sucks. But the advantage is the clumped is probably that like like predators are like less of a threat because you're sort of with all your peoples rather than like sort of like secluded from them, like in your own little, like you're like a lone wolf. You have like your own pack, like, you have your pack with you, so you can sort of like it's easier to fend off predators. And then for uniform, the advantages to that are probably like you get all the resources to yourself that are available to you, but I guess another disadvantage is like predators are a bigger threat. And then for random advantages, like if you're lucky, like you'll have a lot of resources. Okay, now let's go ahead and go to calculate population species effect on one another. Okay, let's see if some of these questions confuse me, so I'll try my best. But let's see. Calculate species richness, number of species from data. Okay, so that'll be like it'll literally give you a diagram. Like this was on the test, I remember, and you'll just have to count. You're literally just counting. It'll give like there's like a diagram and it had different shapes, like different shapes with different colors, like um distinct colors for each of them. There's a better word for that, but I forgot. And basically you're literally just gonna count like the different shapes. And that's how you get species richness. And to calculate species abundance, there'll usually be like numbers next to them, and then you'll just count that and add it up inside that species only. If you're doing it like within a species. If you're doing it for the whole data set, then you're just gonna add all the numbers together. Predict relative species richness. And different. Okay, so I think what this is asking is like different ecosystems. Like let's say a desert. Like not only are there limited resources, there's also like not a variety. Like it's not very diverse. So not only is there not gonna be like, oh, how about like I started that over. More resources equals more abundance, more diversity equals more species. So, or like more richness. So, in like a desert, you're not only not going to have very much abundance, you're not going to have very much richness inside species. But like let's say like the Amazon rainforest, not only is there like a lot of available resources, but there's also there's a lot of diversity inside those resources, like different plants and like that kind of stuff. And so you're gonna not only have more abundance, you're also gonna have more richness. Use data to explain or predict the impact of predators, grazers. Okay, so I think what this is saying, like let's say you have there's the grass. Should I do fish? I'm gonna do fish. That's seagrass, or like sea plants, and then you have like the microscopic organism things. And then you also have the fish. So this is kind of like the hierarchy, the, the food hierarchy. I guess, species hierarchy. So I don't even know if that's right. But okay, so let's say you introduced more fish. Well, what would end up happening is that the fish would eat all of would end up like if you in like okay, so all ecosystems like they'll stabilize themselves. Like there'll be like just the right amount of predators so that they don't overeat, but also so that the grazers and things don't overeat. So basically, let's say you introduce more fish into the problem, then there'll be no more grazers or grazer slash prey. So this will not only will like there be more seagrass stuff, but the fish will also die because they won't have any more of prey to eat because they'll overeat. So that's one thing, and then you're just left with an abundance of producers. The next one is if there's like too many of these things, like this. Um, well then they'll overeat. They'll overeat this. They'll overeat the producers. So then they'll kill themselves. So then they'll kill the fish. So it'll just destroy the whole thing. And I guess another thing is like if there's more of this, then it's just gonna mean that it's able to support more of these things, which means that there's able to support more of these things. So I think introducing more producers isn't that much of an issue because it just means that there's more abundance. Well, something will screw up actually. Like something will screw up. Like this is a very simplified ecosystem. Like it's usually not just three things, it's a lot of things. Like maybe there's like some kind of like other organism thing that only eats these things or like only eats, I don't know, something. Somehow it can mess up, but I think I got the like two important ones down. Okay. Use data to explain and slash or predict the impact of. Did I just did that? I just did that. Okay. Predict and slash or explain the impact of competition on population sizes. Okay. Impact of competition. Okay, so when it comes down to competition, that's just like different animals like fighting each other for different resources. Like that. So let's say like they're both fighting over some delicious meats. I don't even know where I'm going with this. I just wanted to draw. But when competitions decrease, then competition becomes less of a problem. When populations increase, then they become a lot more scarce because now you have a whole nother competitor introduced to the problem. So now there's all these different, I guess, animals competing over the same resources inside of one species. So then, eventually there probably won't be enough resources to support all of it. So like, some of them will kick the bucket, some of them will die. And that's sort of like this thing and carrying capacity right here. Like when there's like plenty of resources to support the population, as you can see here, like there's plenty of resources here, then it'll exponentially rise. But as soon as they go over how many, like the amount of resources that can support that population, they'll start to crash a little bit. They'll start to see like, a crash because they overate, they overconsume their resources. So now they don't have enough to support the population, so then they'll crash and they'll go back down, but then they'll eventually recover and eventually they'll like see like again this is like where so now they're like under the amount of available resources, so then they can still come back. And then it usually like evens itself out over time. Okay. Calculate trophic efficiency. Okay, so for trophic efficiency, this is actually probably like one of the easier ones. I guess for like, it'd probably say like what, like the trophic, just like explain. But at the bottom, you have producers. And then after that, we have the first trophic, tropic, and then the second, and then the third, and then sometimes even a fourth. But eventually, like, there won't be enough energy to distribute, and so there won't be enough to support a whole nother tropic level. So it's actually really easy to do trophic level because all it is just like it's this number. Like, let's say that this number is 100, and then this number is 1000. It's literally just that. That is your equation. And then 100 divided by 1000 is just 10. So your answer would be 10%. It's just like literally like if you split this and then take this number divided by this number, that's your trophic efficiency. So like if you draw it out or whatever, like it's gonna be really easy to see it. What is it? Growth equals food intake as a percent. Oh, I see. Okay, so that makes sense. Is less than 100% and where okay, so energy is usually lost to like heat because animals move, they have to, breathe. And like sort of like on unit 1 we learned that like doing all that requires ATP, and in that process it takes chemical energy and converts it into heat energy. So a significant amount of energy is being lost to heat. I guess I should do it red. Lost to heat. And that's really it. There's also like waste. Waste is also one of them. But the problem is like then there's decomposers and they feed on that waste. So it technically does go back into the trophic in a way. But it's heat. It's where it goes. It goes into heat. Okay, explain why the number of trophic levels is I already did that because at some point the ecosystem won't be able to support a whole nother trophic level because there isn't enough energy to go into a whole new level. Predict the effects if primary production is that like baby making or increased as okay, so if primary was increased, then all the other trophic levels above it would also increase, and it would probably take a good toll on the producers because then there'll be more of whatever feeding on these, so it'll poo it up a little bit. But if the trophic level were to decrease, then all the levels above it would decrease. And if this one were to decrease by like let's say 70%, then so would this one. This one would also decrease by 70%, and so would this one. It's kind of just like hold on. It's kind of just like a chain. But you don't have to do any math except for just do whatever this, let's say it's x, you're just going to do x times 0.7. That's literally, I'm pretty sure, all you do. Okay, analyze the food web, identify the different trophic roles. Okay, so at the bottom, I kind of did this producers. First level, you have herbivores, grazers, prey. Second level, you're probably gonna get hit like omnivores, and then third level, that's probably like carnivores. I think that's actually because like the first level will probably eat most. The first and second levels will probably end up eating most of like the producer, like available producer stuff. They'll eat most of it, which I mean like there isn't enough like vegan food, like not meats, plant food for the third consumers. So like evolutionary, like in evolution they kind of developed to only eat meat because that's all that there was really available. So that's probably what that was. Okay. Impacts of removal or addition of specific species. So if you were to remove, let's say okay, so you have like these are the wolves. And then underneath that are the bears. Oh my god. And then below that are the bunnies. And then even below that is like grass and shit. So if this number were to increase, well, I guess bears aren't really a good example. Well, let's pretend that the wolves eat the bears. If this number would increase, then this number would decrease, which means, well, this probably would also eat this one, which means that it basically kind of what I was going on before. What is that? Top love person in the food chain will overeat their food, so then they'll be left with nothing. And they will kill themselves ultimately. So then you just have producers. But let's say like this one were to increase, and like let's say that the bears, I think bears do eat bunnies, there'd be less bunnies, which means like the bear only eats the bunnies, then there'd be no more bears, which means that there'd be no more wolves. So yeah, and if there were to be more bunnies, then they'd overeat the producer, which means that they'd kill themselves, which means that they kill the bears, which means that they kill the wolves. So it's kind of like that. It's that kind of thing. Okay. Explain the rules of decomposers in what the fuck is a detritivore? Detritivore. Oh, that's a decomposer. Oh wait. Okay. On cycling of energy and matter. Okay. So what happens is like there you have like the trophic levels and whatnot, and then each level, not actually maybe even producers. Yeah, even producers. They all have their own, like they all basically let out their own amount of waste. Of course, this one's probably gonna have more waste than this one, but that's not really important. And then there are the decomposers. This is a worm. It's a decomposer. And what that's gonna do, hold on. What that's gonna do is it's going to eat up the waste, the poo, and then it's going to send it back into the atmosphere as carbon. Yay, go decomposers. So that's what they do. And it's also gonna like I want to say it's almost gonna like recycle that material back into like the soil, which is gonna go to the producers, which is gonna help the whole entire chain. So decomposer is very important. Okay, where was I? Explain the process that cycle water on Earth and living a cycle. Oh, okay. So this is on the Mr. G'day test. There's probably gonna be like a diagram if it gives you this question, but like trees is transpiration when it sends water up. There's like surface runoff, there's precipitation, which is raining and snow and all of the above, and then there's evaporation, which is water going into the atmosphere, and then there's groundwater, which is there's like percolation, which is the water actually like it's like groundwater, and then there's the groundwater transferring back into like the ocean. And then there's more like it's like precipitation over oceans, precipitation over land, surface runoff, blah, 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 blah. And then there's rivers too that send it back on to the ocean. So very, very cool. Process of cycling nitrogen on Earth. I think I did this in my first video, and I don't want to do it again. But that's just like there's nitrifixing bacteria, nitrifying bacteria and whatnot. And then sorry if you can hear that, I'm sorry. And then basically all that does is it just it makes more nitrogen available to like the plants in the soil. That's what that does. And then it's also like waste. Maybe not. Oh yeah, it's waste, because then decomposers eat that and then it's like spit out nitrogen. stuff like that. There's also probably going to be a diagram for that too. So that's very cool. Okay. Covered in previous unit. Cycle on Earth. Explain the processes that carbon cycle on Earth and the role of living things. What the? Explain the processes that carbon on Earth. Of carbon. That's like process. Carbon. I forgot the cycle. Explain the processes that cycle carbon on Earth and the role of living things. And yeah, we already did that. That's literally what I did. Oh, is this like nitrogen? No, that's like the same question. It's fine. One's nitrogen, one's carbon. It's fine. Oh, last unit already. Wow. Effects of disturbance on otherwise stable complex ecosystems. Describe different types of natural and human-caused disturbances. Natural caused things is probably gonna be like natural disasters, like fires is a big one. Like there's, because that leads to like, it's not sedition, is it? Succession. Like natural disasters, floods and stuff, etc. But honestly, like floods can technically be human caused because we're putting carbon into the atmosphere, which is melting like the oceans and stuff, which is rising sea levels, which is causing floods. So some of those disasters are actually going to be human caused, which is important to realize. A lot of those disasters actually. It's interesting. Huh. But human-caused disturbances, there's a lot, like, there's a lot of videos or, like, things of, like, it was, like, the 1900s, early to mid, and we do a lot of, like, messing up with habitats. Like, there's, like, that video when it was, like, the early 1900s, and, like, we tried to stop forest fires, and it led to, like, an accumulation of, like, burnable fuel, like fire fuel, just accumulating in forests, and eventually there was like a really big forest fire. So there was that, and then there was also another thing. What was the other thing? Oh, it was like, I watched a video on this actually. Like people tried to like move beavers and stuff. No, that was an experiment. Never mind. No, it wasn't. In like the mid 1900s, like beavers were getting in the way of like fishing stuff, so like they relocated the beavers. They like literally put them in wooden boxes and they parachuted them out of like planes and just set them and sent them to wherever. But like that's an example of like moving like an important part of the ecosystem, like like disturbing that ecosystem. I hope that makes sense. Oh, you know what? It's probably these things. That's what this is asking. Explain the negative impact of urbanization on biodiversity. Okay, that was kind of when you did that, but like, especially like urbanization, like cities and stuff. Like, some animals thrive, like pigeons. They're doing pretty well in urban areas, but like things like squirrels, not so much. Like they're getting run over by cars and stuff, and it's sad. So, it's things like that. Like us urbanizing in certain areas is sort of like like when chopping down all the trees in Australia and stuff, like we're getting rid of like koalas habitats, so that's like limiting their population, their carrying capacity. Explain the relationship between habitat size and species richness. So the impact of habitat what's habitat fragmentation? Is that like splitting up? Why is that? Oh, that's like the fucking koalas I was just talking about. Probably just less diversity in a certain ecosystem. That's what this will lead to. And a smaller species is also like those fragments won't be able to support as great large species. So habitat size equals more resources, which equals bigger carrying capacity, which equals more abundance, and habitat size also equals more diversity, which equals more species richness. Explain how how ecosystem complexity, I see, relates to ecosystem resilience. Okay, so ecosystem complexity resistance. So that's a I don't like how that's phrased. I do understand it, I think though. So having more having more species, ecosystem complexity, which I'm guessing just means like like they're the producers, but then there's like the prey, but then there's this thing that only eats the prey, but then there's this thing that eats this and they eat the prey, but then there's this thing that eats that. I think it's like saying something like that. It's like what ecosystem complexity is. And basically that means is like when one population is like struggling or crashes a little bit, then or like one species, another species will still be able to survive because they have other resources that they also can use and depend on rather than just depending on one. I think that's what that's saying. I hope that's what that's saying. Okay. Explain how and why primary. Different. Okay, so primary succession is when you're starting from bare rock. No soil, just bare rock. And in that process, you'll get lichen, which is like it's a weird mix of stuff. It's algae and it's like moss. It's a bunch of stuff together, and that's what sort of like creates really rich soil and stuff. While secondary succession is probably what you're gonna see after a forest fire. You're gonna still see some soil, which means that it's not gonna have to start from rock. No, from it's not gonna have to like start from zero. I forgot the saying. It's not gonna have to start from nothing, so it like has something to work off of, and that will like it'll of course develop quicker. Not like at a faster pace, but it'll just have like a head start. Predict and explain how rates of disturbances. Okay, I can't sing and comprehend what this question is. Predict and explain how rate of disturbance affects the types of organisms seen in an ecosystem. Okay, so rate of disturbance. I'm guessing that's like either that's like I don't know, like maybe this like going back to koalas, like maybe the speed that the trees are being cut down, or that could mean like just overall like disturbance, the rate of disturbance, sort of. And types of organisms seen in an ecosystem. So again, like less resources means less carrying capacity, which means less, less populations, which could also mean less complexity within an ecosystem, which could like sort of like limit the amount of organisms available in an ecosystem, and maybe even end up sort of like completely eliminating. Well, it will eliminate species if you're considering like the complexity, because maybe I should do this better. Like there's more disturbance, so there's less grass, so there's less of these things, which means that this thing might not be able to even exist because there's not enough of these things to support because there's less of this. So it's kind of like that. I hope that makes sense to you. To you. Yep. Describe and explain different types of species found in human disturbed locations such as urban areas. So pigeons are a great example of this. They've successfully adapted to urbanized areas. They've learned how to sort of like, same with seagulls. They like, have learned to just eat the food that we litter everywhere. Things like that. And I guess birds are a good one because they can fly. So like cars aren't really seen as like a big threat to them because they can fly away rather than a squirrel who is stuck on the ground and, I don't think they're smart enough to predict the, the acceleration or velocity of like a car coming at them, so they can't predict like, oh, like I'll be able to make it, or like no, I won't be able to make it because they won't be able to know when the car's coming. So squirrels are gonna have a harder time because they're more likely to get run over than birds, because birds can just fly away and they have like a less likely chance of getting hit by a car. Yes. Okay. I'm sorry, I just burped. Analyze and explain the relationship between succession time and biodiversity. Okay, so succession time. So when you're starting from nothing, first degree succession, you're going to. Oh, wait, I might have to, wait, I might be on the wrong track here. Okay, maybe it's asking like succession time. So like as like the the succession progresses and like the habitat begins to like, become more and more mature, there will be more diversity. So there'll be more biodiversity. So it's kind of like that. So I guess that's what it's asking. I hope. Okay, so that sums up everything in this unit. Great job, guys. We did it. Mm. There's also the pear deck. I should go over these slides and stuff. Wow, I like looking at people. Okay, so vocab, abundance, speech. Know that, know that, know that, know that, no, 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 know that. We know that, we know that, we know that, we know that. Okay. Boon stabilize here. Okay, I see. There's one more thing I could mention, and that'd probably be like this is unit 2. It would be like the like growth efficiency. So that would be like the amount that they increased over the amount that they originally were. And then there's also like the change in the rate, which would be new minus the original divided by the original. That's what that would be. So yeah, great job. Goodbye.